We're going to continue now with our treatment of chemical equilibrium and talk about non-equilibrium states. And in particular, these are going to be states where we start at equilibrium, but we do something to the reaction that removes it from equilibrium, and then look at how it responds to restore equilibrium. So our learning goals are going to be determining the new equilibrium when we start from an equilibrium state that has been disturbed. So what kind of disturbances can we have? I call these perturbations on this slide, but what can we do that changes a reaction so that it's no longer at equilibrium? Well, we could add reactants or products to the mixture. We could remove reactants or products from the mixture. We could change the temperature, or we could change the pressure. All of these will have an effect. We could also dilute a reaction mixture, and believe it or not, that can change things and remove it from equilibrium. So these are all ways that we can disturb a reaction. In this particular video, I'm going to focus on the very first one, but we'll talk about some of the others in the next video. Okay, I'm going to go with a really simple reaction. A plus D, B goes to C plus D. All of my coefficients are 1 because I want to make the algebra a little simpler in this. So we're going to start with this reaction system at equilibrium. So Kc is equal to the product of the concentrations of C and D divided by the concentrations of A and B. Now I'm going to involve several actions here that will be intended to change this from an equilibrium system. So my first action would be do nothing. Reaction stays at equilibrium. Well, that's really boring, so we're going to do something else. The second action would be to add reactant A. Now what does this do? It's going to increase the denominator. Okay, so now remember QC has got the same expression as KC in all this. So if I've added something to A and everything else is at equilibrium values, then I've increased the denominator and I've basically caused a decrease in the value of QC so that it is less than KC. Now we know from the last video that when QC is less than KC, it's going to go to the right, so we're going to form more products. So I want you to bear that in mind. We added reactant, we're going to form more products. So it's kind of like we've added fuel to the fire that makes the products by adding a reactant. The same would be true if we added some of B. Now what happens if we add some of product C? Well, in this case, we're going to be increasing the numerator of the expression for QC. Okay, so that means we're going to be making QC greater than what the value of KC would have been. So if QC is greater, now our little arrow points to the left, so we're going to have to produce more reactants. And the same is going to be true if we added more D to this thing. So notice this trend. Add A, we go to the right to form more products. Add C, we go to the left to form more reactants. So now I want to see how this leads us to find a new equilibrium state with our special reaction A plus B goes to C plus D. Now I'm going to give you the equilibrium constant value of 0.833, and one of the equilibrium states would be given by these concentrations. I say one of because there are an infinite number of them. You can plug these numbers in to the expression for the equilibrium constant and you should get 0.833 when you do that. Now, to disturb this reaction, I'm going to double the concentration of A. So I'm going to raise it from 0.15 to 0.3. Now, we know from the previous slide that adding A means I should result in more products forming. Okay, I'm emphasizing this because I want this to be an expected result. All right, so now our new concentration of A is 0.30. So now I'm going to set up my ICE table. I know what my concentration of A is, and my concentration of B, C, and D are the same as they were previously. I haven't changed them. Okay, what about the increment of change? Well, I've got, again, through my own choice, I have a reaction where all of the coefficients are 1, so my increments of change are minus x and minus x for A and B, plus x and plus x for C and D. So now when I add these two rows together, I'll get the equilibrium expressions for the equilibrium concentrations of each of these species. Now if I plug this into the formula for the equilibrium constant, it looks awful, but you know what? Wolfram alpha doesn't blink an eye when you stick this in there, and when you do that, you get these results. Now, notice that there's two answers here. Which one should I choose? I've got negative 7.12 and I've got 0.041979. Well, if I plug the first value for x in to the expressions that I have in my E row, I'm going to have a really large concentration of A and a really large concentration of B. I'm going to have negative concentrations for both C and D. I can't have a negative concentration, so I can throw that solution away. It does not matter. It has not got to be the right answer. It's the other one, the 0.0419. That's the one that I really need. So I'm going to use that now to calculate what my concentration of A would be. In this case, it's 0.3 minus 0.042. That's 0.258. I can do that for each of the other concentrations there. And what this means is I have a new equilibrium condition for this particular reaction. I invite you to go ahead and plug those numbers into the expression for the equilibrium constant. Make sure that you do get 0.833 back when you do that. That's a good way to check your work whenever you do one of these problems.